Hello everyone, welcome back. Today we've got another P5js coding video. So what we've got today is pictures and particles, particle pictures. Basically what we've done is we've loaded up an image and we've used that data to place particles on the screen, and as you can see they try and run away from your mouse and try and get back to where they're meant to be. So if you want to see how we did it, grab yourself a code editor, maybe a cup of tea or your favorite brain juice of choice, and let's get into it. Alright, so we've just got a blank P5js sketch here, and I think the first thing that we're going to have to do is create a class for the particles. So if you saw my last video where we were doing Perlin flow fields with particles in it, which you can see up here, we got away with just using a vector for each particle, but I don't think we're going to be able to do this in this case because the particle is going to need not only an XY location, it's also going to need to know where its home location is so it can make its way back there. So in the constructor, we're going to pass in, just for the moment, it'll just be an X and a Y location. And then we can say this.x equals X, this.y equals Y. And then we also want to set this.home X equals X and this.home Y equals Y. And so that will just set the home base for where this particle wants to return to each time. So if we just start with, actually one more thing that we're going to want, I just remembered, is a color. So we'll store that as well. Okay, so we'll just start with this and we'll see how we go. So we're going to need an update function eventually, but we'll get to that in a moment. And we're also going to want a draw function. And in this, for the moment, all we're going to do is put in a point at this.x and this.y. Actually, we might make it an ellipse. We'll do an ellipse, and we'll say, I don't know, 5 and 5 for the size. Okay, now, I guess what we'll do is we'll just say let p, and then in the setup function we'll say p equals new particle, and we'll give it an x and y of width on 2 and height on 2. Okay, and then what we will try is, we need to give it a color as well. Sorry. Color, and we'll just say, I guess for the moment we'll just go with black. And then in the draw we'll say p.show, or did I call it show or draw? Draw. So p.draw. And so if we run this, we should just get a dot in the middle of this field. So we passed in a color, but you can see it's not actually using it. So what we will say is in the draw, we'll say fill this.c, and that'll set the fill color to the color that we gave it. And so now when we run it, we should get, a black dot in the middle of the screen. So that's good. Now what we need to do is we actually need to update the particle so it reacts to the mouse and is repelled by the mouse and then attracted back to its home location that we stored up here. So in the update function, we're going to have to calculate a few different things. So what we're going to need to do is calculate the distance from the point to the mouse and also the angle from the point to the mouse. And then we're also going to have to calculate the distance and the angle of the point to its home location. And then we'll use both of those bits of information to generate a velocity that we're going to add to the vector, to the particle's x and y position each update. So to get started with that, we might figure out all the mouse related information first. So we'll say let mouse d equal the distance between this.x, this.y, and mouse x, mouse y. And then we can say, so the distance function in P5 just gets you the distance between 2 points. So in this case, the particle and the mouse. And then we're going to say for the angle, let mouse a equal a tan 2. So a tan 2 is just a trigonometry function that gets us the inverse tangent, which means given the 2 points we've got, so the mouse point and the location of the particle, it can give us the angle in between those two. So, and with this function, the y coordinate actually comes first. So we'll say mouse y minus this dot y for that, and then for the x, we'll say mouse x minus this dot x. Okay, and I think that's all we need for the mouse for the moment, so we'll move on to the home stuff. So let home d equal, actually we can probably just copy and paste this and modify it. So the home distance is the distance between this dot x, this dot y, and this dot home x, and this dot home y. And I'll just scooch that across. And then for the distance, we'll say home distance, and then instead of mouse y, again we've got this dot home y. Oh, sorry, this is the home angle. And instead of mouse x, it's this dot home x. Okay, so that's got us the distance and the angle between the 2 points that we need. Now we need to figure out, given this distance and angle, and given this distance and angle, what forces are we going to apply to our particle? So let's say actually I'll just make a little comment here. This is the forces. So let the mouse force equal, and so what we want to do here is we want to say, essentially, if the mouse is within a certain radius, then we want to start applying the force. And we also want to say the force gets stronger the closer the mouse is to the point. So what we can say is we'll say map the mouse distance, and we'll give it a radius of, so it can go between, the distance can be between 0 and, we'll say, I don't know, 100. So once the mouse is 100 pixels away, and then we want to map that to, let's see, so when it's really close, so the distance is 0, we want it to be a strong force. So we can say, I don't know what sort of force to give it. We'll say 10 for the moment. We can tweak this number. And then when it's really far away at 100, we'll give it a strength of 0. And then we'll say a similar thing for the home force, but we want this to be attracting rather than repelling. So home force equals, and again we'll map the home distance, which is also between 0 and 100, to be between, say, 0 and 10. So you'll notice when the home distance is 0, so it's already at home, then it's applying 0 force, and when it's really far away, that's when it's applying the maximum force. So it's the inverse of what we were doing for the mouse. So now that we've got these two forces, we can apply them to our particle. So what we can say is let the velocity in the x direction equal, and now we're going to use some more trigonometry to convert these sort of polar coordinates back into Cartesian coordinates. So we're going to use the cos function, and we're going to say the cos of the mouse angle. So the cos function essentially gets us the x component of an angle, and so we're passing in the angle to the mouse, and we want to times it by the mouse force, and then we want to say, we want to add on the other force, which is cos of the home angle times the home force. And so we're adding these two different forces together, which should produce a net force in the direction that we need. And then we can do the same thing for the y. So let Vy equal, and in this time, because we're using the y component, we're going to use the sine function. So I'm going to pass in mouse A and times it by the mouse force. And then we want to add onto that the home angle times the home force. Okay, and so now this Vx and Vy should be the velocities that we need to apply to our location, given the distance from the home and the distance from the mouse. So it's as simple as now saying this dot x plus equals Vx, and this dot y plus equals Vy. So now if we save this and run this, we should hopefully see, as we bring our mouse in, nothing happens. So let's try and figure out what's going on here. Oh, I think it's probably because we're never calling update. So p.update in the draw loop, And if we run that, you can see that the point disappears. So that's not what we want. And I think, so I think what's happening is this map function, even though we gave it a range of 0 to 100, I think it'll extrapolate. So we might just want to constrain this force that we're getting to be between 0 and 10. Okay, and if we try that now, yeah, so it's staying in place, and so as you can see, we're getting an attraction to the mouse and an attraction to home. So we've got half of it working. So you can see it's coming home fine, but it's getting attracted to the mouse. So in order to fix that, I think there's a few ways that we could go about this, but I think that the easiest way would just be to actually, so essentially the mouse angle, the direction we're applying the force is 180 degrees around from where we want it to be. And so the easiest way to fix this, I think, is just to swap in this a-tan function, we just swap which way we're getting the difference. And so now if we run this, we should see that, yeah, the particle's repelled by the mouse and it's attracted back to its home location. And actually we can probably visualize this better if we say, if we give it just a little bit of a fill and say the same for the stroke, and we draw an ellipse at this dot home x and this dot home y at home 5, and then we can draw a line between this dot x, this dot y, and this dot home x and this dot home y. And so now we should see, you can see a little ghost of where it's trying to get to and the line in between the home point and the actual point. So you can see if I put my mouse right on the location, it's sort of stable, and as we move around, it's always trying to get back to that home location. So now we've got the particles that we want to simulate. So I think what we're going to try and work on now is we're going to upload an image and try and get these particles to create an image. So let's get started on that. So I think, well, firstly, we're going to need to no longer have this P as just a single particle. So I'll call it particles instead, and I'll say, instead of saying it's a new particle, we're going to make it an array, and then we're going to have a function that places all the particles. All right, so, and in order to do this, we're going to need an image. So I'll just quickly upload an image and get right back to you. Okay, so in this little file selector on the left here, you can see I've uploaded a logo image. Unfortunately, you can't see it, so I'll quickly just load it into the sketch. So in P5, we have to use a preload function for things like images, and so we can just say let image, and then we'll say that the image equals load image, and we're going to give it the name, so that's logo.png. And so one thing to note with this image I've got, the background's transparent. And so we're going to be using that transparency to not fill in particles where it's transparent, and we'll only have particles where there's a color. You could also, if you wanted to, make it ignore, say, a background color of white. So if there's a white pixel, we're not going to put a particle there, but I'll show you where that's more relevant once we're actually placing all the particles. So I think firstly, I might just draw the image to the screen. So I'll say image, and we will say that it's the image, and we want it to be, I guess we want it to be the full screen. So from 0, 0 to width and height. And I think, we can't run this because P no longer exists. And we're going to have to put this in a for loop. So for let I equal 0, I is less than particles.length, I plus plus. And we'll just pop that inside there. And instead of just particles dot, we'll have to get particles.I particles.update and particles.i.draw. Okay, and so I think particles won't have anything in it for the moment, but we're just going to make sure that our image is loading in correctly. So if we run this, you can see that my logo is stretched to fit into the background. So now what we need to do is we want to call place particles in this setup function. And what we're going to do is we're going to loop through the image and at certain intervals, and where there is a colored in pixel, we are going to create a pixel and put it into our particles array. Now, one thing to note is that these sorts of particles can get quite laggy if you've got a ton of them. So we might just make it skip a few. So it's a bit of a pixelated image. We'll just skip a few pixels every so often. Actually, we might even define that. So we'll say let resolution, I guess. Let resolution equal, say, I don't know, 4. So we'll go every 4th pixel, we'll draw something on the screen. So what we want to do now is actually place the particles on the screen. So what we're going to do is we're going to loop through the pixels in our image, and if the pixel at that point in the image is a colored one, we're going to create a particle, and if it's transparent, we're not going to create a particle. Quite straightforward. So we'll just loop through for let I equals 0, I is less than image.width, I plus plus. Well, actually, in fact, what we might do, this might be, so since the image's resolution doesn't quite fit the screen, as you can see from the stretched image, what we might do instead is we're going to just loop I through just the width of the screen, and we're going to map that to a position on the image, because where we place the particle has to actually be a point on the screen. So, and actually, instead of just incrementing I by 1, we want to use that resolution variable that we used before. Instead of just incrementing it by 1, we're going to go up by 4 pixels, and then we want to do the same thing for the Y. So let J equal 0, J is less than height, J plus plus, oh sorry, not plus plus, plus equals res, and then what we're going to need to do is we're going to need to translate from an I and J location on the screen into an X and Y location on the actual image, so that we can get the pixel at that location. So I think the way we're going to do this is we're going to say let X equal, and then we need to figure out how far along the screen we are, and then map that to how far through the image we should be. So I divided by the width will give us a percentage of how far along the screen we are, and so then we can just multiply that by the image's width, and that will get us how far through the image we are. And we can do that for the Y as well. So J divided by the height, and we'll times that by the image height. So this will get us the position, so X and Y is the position in the image, and I and J is the position on the screen. So then what we want to do is we want to say, we want to get the color of this X and Y location. So let C equal image.get X and Y, like that. And so that'll give us the pixel values for that location on the screen. And what that's going to return to us is actually an array of 4 values. So in this array, there will be the first one will be the red, and then the green, and then the blue, and the last one will be the alpha, which is how transparent that pixel is. So this is what I was saying earlier, is I'm going to be doing it based on transparency. So if the pixel's transparent, then I'm not going to draw it on the screen, but you could do it for any color you wanted. If you wanted to only draw the not white pixels on the screen, or ignore all the orange pixels, you can do that just quite easily with this. So what I'm going to do, like I said, is ignore transparent ones. So if the 4th pixel value, so the alpha, is not equal to 0, then we're going to create a new particle. So I'm just saying if the pixel isn't transparent, then we're going to put a particle. But like I said, you can play around with what rule you use here. So if we have got somewhere that we want to put in a particle, we'll just say particles.push a new particle, And we're going to use the I and the J values here because they are the location on the screen. And we're going to give it a color of the pixel that we've just gotten from the image. So we're going to use the image color to color our particle. So now what I might do is, in the drawer, I'll just quickly comment out the image so we can hopefully see our particles on the screen. And if I run this, we should get we get a very laggy version of what we want. So, like I was saying before, if we've got too many of these particles, it can run quite slowly, as you can see. So I might just bump up the resolution value, which doesn't make a lot of sense because we're making it less, we're lowering the quality when we increase the resolution. But there we go, that's running a lot smoother now. And I'll just turn off the bit down here where we were adding in the lines and the location of the home on of each particle. And we've still got an outline, so I might just, in the setup, I'll say no stroke to remove the outline around the particles, and I think we've got our final product. So like I said, in this code there's quite a few places where you can play around with things. So you can play around with how strong the forces are that are attracting and repelling these particles. You can play around with the different colors and how you load these particles in. So you could try using text, or you could try using sound to maybe place these particles on the screen. I'll have a link down in the description to this P5js sketch, and you can play around with the code, or if you coded along, I hope you enjoyed this tutorial. So yeah, thanks for watching, and I'll see you next time.